First, let me thank the organizers for getting us here. And I would like to start with, okay, I got it, okay. And I use mine. With clarifying, there's two Jias over here in this meeting, and we date back for 20 years, and we both, we have the same set of affiliations in China and University of Michigan and UCLA. So we are planning to stay here to confuse you guys. Well, my talk is changing into those puny magnetospheres, or like the puny worlds. So this is Enceladus, and it is done by this group of people with references to a lot of others around the world. So the baseline of this study is I'm showing those numbers in case you are a theoretist and you want to think of them and fit them in those coupling theory. So Enceladus is at only 4 Saturn radii. It is very close to Saturn in the inner magnetosphere, and the Saturnian co-rotation plasma is subarvinic. It's what we are dealing with is the coupling between the Saturn magnetosphere and the Enceladus. So here I'm emphasizing this coupling. Theoretically, you would, if there's two bodies, you would be expecting the ionosphere of Saturn, the magnetosphere of Saturn, and the magnetosphere or ionosphere of the body. But here, this is the mess because it's puny and it's quite different from the Earth's magnetosphere-ionosphere system. For ionosphere, it is we can we can simplify it into the collision frequency, and for a magnetosphere, we can simplify it into the plasma momentum and the field. But for this world, it's so puny that it doesn't have its own magnetic field. So we so it doesn't have any like polar potential things and no seasonal. It's but it's different, but it makes also makes it quite simple. What only thing we left is this Enceladus plume. So in this interaction, well, I put a M or I here because some would like to call it a magnetosphere because it does have an induction magnetic field, and some would like to call it an ionosphere because the collision is quite important here. So there's this collision effect. Well, what we have here is this plume. It is not even a sphere. It's quite different. So only thing left is in our model is this magnetosphere and this plume. The ionosphere is far away. It takes like about 5 minutes for the Alpha wave to go back. Go to the ionosphere and back, and the plasma would already passed this moon. So we are, for this local interaction, we are not considering the ionosphere at this moment. And for the magnetosphere, we are simplifying it into the density only. At the later stage, I will show you some variations in the velocity also, so this U. But here is only this plasma density and this plume, and so because it's simple, it also gives us this opportunity to from all those measurements to detect this plume and this density, and this density is clustered in the Enceladus torus. So now this problem is simplified into this M and M interaction, and I hope that they can wish you a happy Valentine's Day today. A problem here is an example here is that when Pryor et al. Looked into the Saturn aurora spot from Enceladus, they claim that the spot has like twice the intensity variation during their observation time. But I would argue that that variation is the effect of this total coupling. It's not. They think that it reveals the Plume variation by a factor of 2. But I would argue that it is the total of this interaction that is varied by a factor of 2. It's not the Plume itself. And please keep this M and M coupling in mind, because I will be mentioning it a few more times, and they're happy. So the first part of this talk is the Plume. Because it's the source, so we started the Plume at first. Cassini has visited the Enceladus many times. Now we have 20 flybys, and you can see from all those trajectories in those 3 planes, plane cuts, you can see it's a pretty good coverage. What I'm plotting in color here is where we see the large magnetic field perturbations. So you can see the Plume has its effect in these regions, and that's how we represent the Plume. So in the earlier stage, we modeled the Plume. We used the same Bastrats code, simulated this local interaction with the magnetospheric plasma and the torus plasma and this Plume gas pickup. We use those agreement to identify the intensity of the Plume. So this is how we got. We need the information of the torus plasma. This is got from the RPWS group. They measured the plasma density in the torus close to Enceladus. So there is large variation in the torus, but we see much smaller variation in the Plume. And then we put those variations in terms in this distance, because recently there is a paper looking at the microwave band reflection of the Enceladus Plume. They have seen very large variation in the Plume brightness. Why I have this thing here? Okay, better. So this group, they have found when the Enceladus is at its farthest on its orbit from Saturn, the Plume intensity is much higher. But when we plot this red spots are what we get from the neutral Plume. When we plot it here in the same coordinate, so those green lines are the average, the semi-axis. This is the Paris axis. Those two are the axis. We don't see this much difference. And if we plot the torus density, we don't see the variation either. I guess that they are looking at the dust, and we are looking at the gas and the plasma. So there are two questions now. Why the dust and the plasma and the gas are giving different variation conclusions, and also why are the Plume not changing much, but it is creating a torus that is changing much. Let's look at the dust and the plasma first. So fortunately we have like those four flybys very close to each other. Those two are the plotting the trajectories in those two planes. So this is Enceladus. These are the four trajectories, almost the same. But if you look in the XY plane, which is below Enceladus, the plane parallel to the Enceladus equator, they are passing, most of them are passing through the center, and only this E19 is passing upstream. So if you look at the magnetometer data, E19 is not is showing very different signatures from the other three. Those data are detrended from the B total, and the most of the magnetic field in this is in this BZ component. So the BZ is about the B total. I'm only showing the variation here. So here you are seeing the those three trajectories. They are penetrating the center of the plume, where the ionization effect is strong enough to exclude a little bit of the field. But this By is always a problem for our simulations. Now we understand that it is caused by charged dust. And if you look at the difference, the magnitude here, I'm not blowing it up, but I can read it for you. This E14 black line is the minimum. But if you look at the dust signature, which is represented by By, it has the largest. So that's why we think that maybe dust production is has a larger variation, while the plume variation is still stable. And this is still the same set of data, but we are looking at the ion cyclone wave here. The ion cyclone wave, now we are talking about that M and M coupling. So ion cyclone wave is giving you the information of the total pickup. So it has the information of both the upstream and the local pickup. So we are seeing that E14 is the minimum. Also, it agrees with the B total, but we are seeing E17 and E18 much larger. Now, if we look at the location, orbital location of Enceladus when those happened, it also doesn't agree with that this arrangement. So my conclusion is that from those plasma data, we don't see the same variation along the Enceladus orbit. Now the second part is let's take a look at the wake. Now I raised the question that why the wake is the plasma density varying this much by a factor of 2, but we are still claiming that the plume is stable. So here is one wake flyby. Let's look into the closed wake first. So this is the only flyby, but I find it very interesting, and it gives us a lot of information. So what I'm plotting in color here is still the magnetic field perturbation. So we are seeing the B total increase in this location, and the BX/BY perturbations in this location. So the upstream flow, the co-rotation plasma flow is coming from this side. So it's going this way. So this is the geographic wake, and this blue dotted line is what we think the wake is. The reason we think the wake is not only we found the magnetic field B total in this location, but also we looked at the MIMI data, the high energy, both the high energy electron data and this RPWS again, this electron density data. So this wake align very well with the magnetic field increase. So the field enhancement here is that when the the pressure in this region is lower, and the field get pushed in to compensate the pressure. And if you look at the higher energy data, you also see those absorptions. So what we think is that we are seeing the absorption wake from the moon. When the plasma is coming this way, we are seeing the plasma is absorbed along the field lines into this plane. When after it passed, it gets to this place. And now the question is, why is this wake shifted from the Enceladus orbit, and why are those signatures shifted inward? So this is our model. I'm presenting it in a reverse way, but this is those are the measurements. But I will show our model, our interpretation later. If you look at all the Enceladus flyby data, okay, you will see that the field enhancement is in this location and the decrease in this location. And if you look at the arrows, you will see those field perturbation going this way. Those arrows are the orphan wing created by the orphan wing field line currents. And traditionally, you would think they are piled up from the upstream and decrease in the downstream. Now, why are they rotated in this direction? In the past few years, we have figured out it's done by the charged dust. So when the charged dust has their mass is about 10,000 times the proton mass. So their gyro radius is about 40 Enceladus radii. If you look at the plasma locally, you don't see their movement, their guiding center movement. So when they are moving along the electron field, the plasma, the ions respond to that movement in a different way that you treat traditionally in the plasma, where using guiding centers. So that the plasma are moving in this direction. So those blue lines are what we draw as the electron stream lines. So the electrons are carrying the flux tube outward. And the explanation to those inward shifting BX, BY perturbations is that this whole system is rotated. So you're seeing the part of the transversal effect in this location. And now this is the second part of our work to study the Enceladus wake. So we have seen those transversal perturbations close to those flybys. They are there sometimes, and those are a set of very close flybys also. So, but sometimes you see them, sometimes you don't see them. Don Mitchell are like associating them to those energetic particles along field lines. And we know that this is the spectrum of uncyclotron waves. We know that they are not uncyclotron waves. They are not too close to be the orphan waves that is bouncing back from the ionosphere. So I'm not sure what they are, but we use those transversal waves to track the wake of Enceladus. And we do find a lot of them along the wake. So yeah, this part of the work has been started by Jared Leisner when he was still a student at UCLA. Now Han-Ying picked it up, and she looked at those all those Cassini rev data around Saturn, and she found a lot of those events, and she plotted them together. She see the location of the events. Most of them are falling away from Saturn, and some of them are falling close to Saturn. So this positive means away. This is showing you the criteria that we use. We tend to limit those events closer to the equator to avoid the false alarm from those high latitude field line currents. But we did correct them, their location into this L shell using the accretion model field model. There are a few working on there are two groups actually seeing the electric field in the inner magnetosphere of Saturn, and so we looked into those variations, trying to see any relationship between this radial variation of the wake with that local time, because the electric field is found to be aligned with fixed to local time, but we do not see any association. So our conclusion is that the wake is waving in and out, even in this very inner magnetosphere. So that's why we see the plasma density at Enceladus is changing by a factor of 2, even if we think the plume is not creating a much large variation. But what I really want to say beyond this talk is that there has been a lot of work trying to determine the variability of this plume. And if I list the work that is trying to determine the plume itself and the momentum, the mass loading rate of the plume, it will be go on beyond this paper, beyond this page. So I'm hoping that we can get funded someday and put everything together on the table to solve those differences. Yeah, thank you.
All right, we have some time for some questions.
I didn't quite follow your argument for why these transverse waves were not Alfvén waves or EMIC.
They are Alfvén waves. They could be Alfvén waves, but they are not the same Alfvén wave that is propagating from the moon to the ionosphere and then back. That's too short. But they are Alfvén waves. I think they are Alfvén waves. Until I get the electron and the CAPS data, I cannot cannot compare them with those interchange events. But I do think they are Alfvén waves.
Okay, thank you.
Yeah.
Have you used the deviation of the plume of the wake to figure out a velocity, a radial velocity?
Oh yeah, I think you know that the CAPS team has seen the variations of the radial velocity and the magnitude of the velocity as the Enceladus orbit. But in my first so in this model, we do have an explanation why the plasma velocity has a radial component, radial perturbation driven by the charged dust at Enceladus. But
It's the same order of magnitude as what's
I haven't compared them. Yeah, but because this model I haven't used it to even fit the plume yet, so I kind of use it to fit the global velocity. Yeah, I'll keep working on that.